Hi, can you hear me?
Yeah.
Okay. Okay, so we are going to start a new topic today, which is inversion and poles and polars. So this will be the last topic in geometry before we switch gears to something else like maybe combinatorics or algebra. But before we get started, just want to briefly recap on last week's test. So I've shared the evaluated answer script with you. You can take a look at your own performance. But just want to give some general ideas. I mean, looking at I'm not going to discuss the objective questions. I think those you can figure it out. But mainly on the subjective ones, there are a few common mistakes which students have been doing while either in their logic or while presenting on the paper. So I just want to mention them so that next time you solve subjective answers, you try to avoid those mistakes. And also, I can briefly discuss the questions also because I think there are some interesting alternate solutions available there. Okay, but yeah, just give me 1 minute. Okay, so I hope you can see my screen. So yeah, so starting with question one, I think many students have made a mistake of trying to use Seva's theorem for this question. So I think there is some basic understanding that you need to get clarified that when you can use Seva's theorem and when you cannot. So the question was about the eccentre I1 and the perpendicular from I1 to the side BC, and similar lines from I2 and I3. So those were the ones you have to show concurrent. So trying to use, this point is B. We actually we know that BD upon DC and this product is equal to 1. This is known. You may have done this in your regular lectures. And that what that means is the lines AD, BCF, they are concurrent. But the question was not about these lines at all. The question was not about AD, BCF. The question was about these perpendicular lines. So these lines being concurrent has nothing to do with Seva's theorem, or at least not in triangle ABC. Okay, so that is one common mistake which I found in a couple of papers which I evaluated. Okay, so cannot use Seva's theorem, at least not in triangle ABC. You can still use Seva's theorem in triangle I1, I2, I3. So that will be actually trigonometric form of Seva's theorem. So in the triangle I1, I2, I3, what you can do is so the line which you're interested in is this one. So if you look at the angles formed here, so if I call, in fact, this angle is exactly C by 2. By some angle chasing, you can see that. and this angle will be b by 2. So if you write the sign of like the sign of angle CI1D upon sign of angle DI1B, etc. So this product will cyclically be equal to 1. And so that is how you can use trigonometric Sevas theorem in triangle I1, I2, I3. So that is valid, but not Sevas theorem in triangle ABC. So this was one mistake which, if you are making this mistake, just make sure you have the concept absolutely clear that when you cannot or cannot use a particular theorem like Sevas theorem or any result for that matter. Okay, so that was one thing. Another thing, so a couple of people use Carnot's theorem to do this problem, which is valid. So Carnot's theorem does give us the solution because basically the BD of what you have is a triangle ABC and 3 perpendicular lines. So it is enough to show that BD square minus DC square plus that whole cyclic summation is equal to 0. And so this is one of the typical expected solutions because we know the lengths DD and DC, S minus A, etc. All of those things. But just one minor point there is whenever you use a theorem like that, it's important to clarify in which triangle you're using Carnot's theorem. Just writing this expression directly is not the best idea. At least you should write that in triangle ABC by Carnot's theorem, etc. So some context has to be given whenever you use a property. In which triangle, what are the objects which are using to apply that property? Okay, and you can check my solution for some idea how can you write your answer better. My solution is not perfect. There are a couple of things to improve there, but at least you will get some reference point. Okay. Then one more case I found where somebody has just written that with some angle chasing we get so and so. So the phrase with angle chasing is very vague. We have to explain what is the angle chasing you are doing. You have to write out what is the exact order in which you are doing the angle chasing. And also many times what I see students do, they don't make the markings on the diagram. So they mark the equal angles, etc. on the diagram. That is okay for your rough work, but basically when you mark in any diagram, let's say I make any markings, whatever it be, X, X, O, whatever. I don't know in what order you derived those. Like, did you first write the X or first the O? So, the logical sequence of proving one step after the other is not clear when you just make markings in the diagram. Okay. So, those markings are useful as reference, but you still have to write the proof that first I found this angle equal to this angle, etc. Whatever is the chain. And you don't have to justify every step also there if they're like obvious steps, like if it's an isosceles triangle, the two angles will be equal, or in cyclic quadrilateral. So, yeah, you can take some liberty there if you want to save time, but you have to absolutely write the argument. You cannot just say with angle chasing I got so and so. With that logic, I can write by solving the equation, I get the final answer. So I can directly write the final answer. So that is not valid.
Sir?
Yes?
Sir, I solved this question using the trigonometric form of Sevas theorem in triangle I1, I2, I3, and
Okay.
I have written exactly as you have just explained, but you have not
Okay.
put any marks.
Okay, I'll take a look at your paper again after the lecture. Yeah, so anybody else also has any discrepancy with the marking, you can message me either on the group or directly. So I will take a second look at your paper. Okay. Okay. So then apart from this, I think one more mistake which students have done. Again, it's not a mistake, but from the point of your presentation, the diagrams have to be drawn with pencil and accurately. So you cannot make a, just for example, what I'm drawing on the tablet right now, like a pen, rough sketch using a pen, that is again okay in the rough work, but not to be done when you present the question finally in the fair solution. Okay, so in the fair solution, you have to draw an accurate diagram with the pencil. Okay, this is a must. And then also somebody had written the entire paper in red ink. So red and green colors are not to be used to write the actual text. You can use red and green color briefly to make markings in the diagram. Like for example, if you want to make some angles equal, etc., that is completely optional. Maybe some students find it helpful, so you can do that. But apart from those like small markings here and there, rest of the paper has to be in either blue or black ink. Okay. So I mean that is compulsory, and I mean simple reason for that is the evaluator uses red or green color. So if you are writing your paper in red color, then how will somebody come to know which part the examiner has marked and which part you have marked? Okay, so this is a very important thing to remember. Okay, let me check with your anything else. Yeah. Yes.
So actually, I joined late due to network connectivity issues. So can you explain what you take with on the diagram?
Sorry, actually there are quite a few points I covered. Why don't you watch the recording later on YouTube? So all
Okay.
of my lectures are recorded. Right?
Okay. Yes. Sir.
Okay. I mean, I'm just giving general tips about how to write your exam paper better. Okay. So just
Yes. Sir.
for your improvement. Okay. Yeah, I
Yes.
think so. Question one. Yeah, these are a few points. Now, the actual solution to question one, again, there are two approaches. So one was the Carnot's theorem, which I mentioned. Second was the trigonometric Sevas theorem, and the third one is, I mean, I deliberately gave this question because even if somebody doesn't understand the new ideas that we have covered, like the power of a point or Carnot's theorem, you can do this question with the theory which you already know about orthocenter or in circle, X circle configuration. Because as I hope many of you are already aware, it's a dual configuration in that basically the what you consider your main triangle. So if you consider I1, I2, I3 as your main triangle, then from that perspective, ABC are nothing but the feet of the altitudes. Okay. So actually it is the orthocenter configuration hidden in the in circle X circle configuration. Okay. So if you think of it that way, then what I'm asking, I mean, this perpendicular line from I1 to the base BC, and whatever theory we have covered earlier also, you would know that this is nothing but the isogonal conjugate of the orthocenter. Or in other words, this line I1D will pass through the circumcenter if K is the circumcenter of I1, I2, I3. Okay. Then this I1D will pass through that circumcenter, and then the same will happen from all the three sides. Okay, so that is why obviously they are concurrent. Okay, so in the standard notation, it would be the lines AO, BO, and CO, but here the main triangle is I1, I2, I3. Okay, so again, this is an important idea that the same diagram has two versions hidden in itself. And I mean, another way of thinking about the same thing is that in a triangle ABC, when you, I mean, in the standard configuration of orthocenter, exactly the same way, if I look at point DEF, then for points DEF, the in center and X centers are the points H, A, B, and C. Okay, so this is the orthocenter configuration for triangle ABC, but it is also the in circle X circle configuration for triangle DEF. Okay, so that duality can be utilized here to solve this problem. Okay, so I think those are a few alternate solutions for question one. Okay, then going to question two, there is nothing much to discuss. I mean, I think it was pretty straightforward question. So, and you can look at the solutions to find out the in case you are not solved it. But yeah, just one thing I'll mention again. This is a advice to save some time. So there were two parts, the if and only if part. Right? So basically, the question was if there is a line passing through the center of one of the circles, then PQRS are harmonic if and only if the two circles are orthogonal. This was the question. So, I mean, the only advice I have is that because it is an if and only if question, there are two parts to it. That first, if it is orthogonal, then prove that it is harmonic, and vice versa. So, those who have done it separately, it is perfectly valid. But if you look at my solution, for example, I have done a chain of if and only statements which directly connect this part to this part. So this if and only if something, if and only if something. So there is a chain of statements which are each of them is reversible. I mean that is the most important thing to keep in mind. You if there is any statement like obviously adding, subtracting, multiplication, division, they are all reversible. But taking square or square root, you have to be more careful because we all know that if a equal to b, then a square equal to b square. But if a square equal to b square doesn't always imply a equal to b. Okay, a can be minus b. So if you are not taking square or square root or some particular actions like that, most of the times your chain of operations will be if and only. But if you take that extra precaution, then you don't have to do write part one and part two separately. Okay, in the same part you can finish both sides of the equation. Okay. So that is just something that you can try to use if you want to save time. But as I said, this is completely optional. You can decide. Okay. So then apart from this question 3, so yeah, question 3 was somewhat more challenging, not very much. I mean, the challenge in all of these questions is always I don't give you all the missing steps in between. So in question 3, the it was about the circles which are orthogonal to each other. So centered at points A, B, and C, I can draw circles. Okay, draw them somewhat accurate. Okay, so the 3 circles, I think I call them omega 1, omega 2, and omega 3, such that each of them is orthogonal to the other. And the question was, if you consider the circle with diameter BC, for example, so if I call that circle gamma 1, okay. So then the question was that omega 1, first part was omega 1 and gamma 1 are orthogonal. This was what you had to prove. Okay, so I never gave you this intermediate task to be done, but finding the radii of all these 3 circles. So if I call the radii R1, R2, R3, then you can set up the equations and find the values of R1, R2, R3, and then that helps you to solve this problem. So I did not give that intermediate step, but that is what you have to figure out. That if you want to reach this goal, you want to show 2 circles are orthogonal, then what is the easiest way you can do that? That if we show the centers, so centers are A and D. So I have to show AD square equal to R1 square plus whatever is the radius of this, so A by 2 square. So for that I need to determine R1. So that was the hint there, that we have to somehow determine R1, and it is easy to do because of the orthogonality. Okay, you can get everything in terms of the sides of the triangle ABC. Okay, so that was the only tricky step involved there as such. Okay, and then once you do this part, then the second part is literally straightforward. That once you have proven that omega 1 is also orthogonal to gamma 1, then what do you have? I mean, the circles gamma 2, gamma 3. So gamma 2 is this circle, gamma 3 is this circle. So gamma 2 has center B, omega 2 has center B, gamma 1 has center D, and omega 3 has center C. So these 3 points are collinear. Okay, and because A is the center of a circle which is orthogonal to all 3 of them, then obviously the power of A, yes, probably this is one hint. Many of people have actually computed the power of A with respect to all 3 circles, but you don't need to do that. I mean, by orthogonality, what do you have? I mean, this tangent, right? Tangent from A to any of these circles, this length is equal for all the circles under question. So then obviously the power of A is also going to be equal, because it is going to be square of the tangent. So therefore the power of A with respect to gamma 1 is going to be equal to the power of A with respect to omega 2 and omega 3. Okay, so therefore A lies on the radical axis, and then because the centers themselves lie on the line BC, so the radical axis has to be the line from A perpendicular to the base, so that is the line AH. Okay, so that was the one way to do this question. Yeah. So, but I want to point out something else about this diagram. This is a very rich configuration, as it turns out. There are so many interesting things happening, and part of what you have to learn is once you solve the paper, it's not over. You can spend more time on your own to explore the idea, explore the configuration, find out more tricks, find out more properties related to the configuration and what you already know. Okay, so if you do that, you will find a lot of interesting properties. So in particular, in this diagram, there are already 6 circles. So the circles are like omega 1, omega 2, omega 3, which are orthogonal to each other. Then the circles gamma 1, gamma 2, gamma 3, which are like these are the diameters BC, CA, and AB. Okay. In addition, you can also consider the circles, let's call them alpha 1, alpha 2, alpha 3, which have the diameters AH, BH, and CH. Okay, so if I add those in the diagram, I mean, I get a lot more interesting properties. So basically, I'm talking about these 3 lines as the diameters. Okay, AH, BH, and CH. And in fact, I think I've drawn this diagram in GeoGebra, so I can show you. It's a very nice configuration. Yeah. So, as it turns out, I won't go into details, but there are a total 15 orthogonalities in this diagram. So the blue circles are the ones with the diameter BCCA AB. The orange ones are the orthogonal circle which we have introduced, and the green circles are the one which AH, BH, CH as a diameter. And you can work out the details, but basically between orange and orange, orange and blue, orange and green, blue and green, all the permutations, there are total 15 different orthogonalities sitting in this diagram. Okay, so that is something interesting that you can try and explore on your own. And in fact, in this diagram, I have not even drawn the 9-point circle and circumcircle. There are further connections with that also. Turns out that this orthocenter, right, H. So firstly, if you notice let's take the orange circle for example. So for all the orange circles, the pairwise chords are the altitudes of the triangle. So these dotted lines, and they are concurrent at H. So which means that H is the radical center for these orange lines. So if it is a radical center, it has to have a common power with respect to all the three circles. So if you try to find out what is the value of that common power, so as it turns out, the power of H, so the power of H with respect to any of the circles like gamma 1, so omega 1, so the power is equal with respect to all three circles. Not only that, the power is equal to it is half the power of H with respect to circumcircle of ABC, and it is twice the power of H with respect to the 9-point circle. So as it turns out, the 9-point circle, so power of H with respect to the 9-point circle and these omega 1, omega 2, omega 3 and ABC, they form a GP. So they are in geometric progression. Okay, all these three quantities. So there are some very interesting things which are happening here. And there might be a lot more things also. I just started to explore this configuration a couple of days ago. But yeah, so my point is that it is not just that you have to study something for the exam. As soon as the exam is over, you forget it and move on. Every question is an opportunity to try and discover new properties, new configuration, and who knows what will be useful at any other given time. Okay? So it is always useful to develop your own a treasure of knowledge or skills or properties that you are explored on your own. Okay, if you just rely on what we do in the lecture, then you are limiting your horizon. So I encourage you to try out all of these things on your own. If you find some interesting properties like this or anything, you can share it with me. You can share it with the group. Okay, so that is very important because we are meeting only once a week, and Olympiad is a very big commitment, so we have to put in a lot more time and effort on your own, apart from the lectures. Yeah, I think so. That's all I want to discuss about the last time's paper. Again, as I said, if there might be some mistakes in my evaluation, please contact me later on. I will update your evaluation accordingly. Okay, so I think with that, let me think if there is anything else to be mentioned. Yeah, I think that's all. So yeah, let us start with the new topic, which is inversion, poles and polars. And this is a very nice, exciting topic. There is a lot of things that we are going to discover in this. But in fact, what we are going to do is we are just starting with the basics of a much wider topic called geometric transformations. And we won't be covering that this time because basically what will happen, we'll do a lot of geometry one after the other. So just as a break, I would like to switch gears to something else later on. But keep in mind that there is a topic called geometric transformation, which is also very interesting, which if you are interested, you can read about it on your own also. But we will cover it later on. Okay. So can you raise your hand? How many have already heard of this term inversion? If you know the definition, you know some properties. Any idea if anybody has? Oh, nobody knows anything? Interesting. Yeah, I just thought maybe somebody has heard this term. It is like a very common buzzword in geometry or problem solving in general. Basically, if you don't get a problem for a long time, somebody will come and say, okay, you just apply inversion and that doesn't explain anything, but it seems very cool to say, okay, you apply inversion. So let us explain what is the meaning of this inversion and why is it such a powerful idea. Okay. So starting with the definition. So inversion is also about circles. So we have been on the theme of circles for a long time. So this is a continuation of that. To be specific, this is a geometric transformation. So let me just unpack that phrase first before we go into inversion in particular. Okay. So what is the meaning of a geometric transformation? Formally, you can say it is a function from the plane to itself. So the plane I'm denoting by r square because like a 2D coordinate system, every point can be represented as a pair of real numbers. That is why I'm denoting it as r square. So geometric transformation is nothing but a function which takes every point of the plane into a new point. So the most boring function could be an identity function, which keeps every point fixed. Okay, so it doesn't do anything at all. Every point is exactly where it was earlier also. Okay, but so there is a whole family of functions that we can study, and so that is where we are going to get into the topic later on. So I won't talk more about this right now, but just know that we are talking about the word transformation means that it is some operation on the entire plane. Okay. So in particular, inversion is also one such operation. Okay. And for inversion, what you require is a circle. So, I mean, what are the inputs to this operation? So you require a circle somewhere. So you have some circle with some known radius r. So then the inversion, what it does is, suppose you have 2 points P and Q like this. Okay. So suppose you have points P and Q which are collinear, such that OP into OQ equal to r square. So r is the radius of the circle. So if you have points like this, then we say that P and Q are inverses with respect to the circle gamma. Or rather, I should say Q is the inverse of P with respect to gamma, and you can easily see that if Q is the inverse of P, then P is also the inverse of Q. So in a way, this is like a mirror image, you can say, because P goes to Q, Q goes to P. By the nature of this equation, you can see that if OP is less than R, then OQ will be greater than R. So in other words, every point inside the circle gets mirrored into every point outside the circle. Okay, so this inversion sort of inverts the entire plane with respect to this circle as the boundary. And if you, in particular, if you notice any point on the circle like this one, it will be its own inverse, because obviously OA square, I mean rather OA into OA is equal to R square, obviously. So every point on the circle is its own inverse. Every point inside the circle has an inverse outside, and every point outside the circle has an inverse inside. And now you can start to imagine what happens in this diagram if the point P starts to move closer and closer to the center. So what will happen to its inverse image?
Will go further and further.
It will go further and further. So is there a point which does not have an inverse image at all?
When O is
At the center.
At the center, right? Because obviously the distance is 0, so you cannot take an inverse of that. So all the points in the plane. So so what I showed about the function going from r square to r square, that is strictly not true in inversion. Inversion, the domain has to be r square minus the center of your inversion. Okay? So it's a function from r square minus the center of inversion again to r square minus the center of inversion. So the inverse has no image as well as pre-image. So this is the function of inversion. So at the first glance, it doesn't explain why this can be interesting. Why should anybody care about this inversion function? So for that, I mean, we need to get a better idea about how it affects various objects in the plane. So in particular, we are interested in how it affects lines and circles. So what is the inverse of a line? Or even before that, when I say what is an inverse of an object, I hope what it means is clear. I'm taking the inverse of every point in that object. Okay. So if I have any set in the plane, any object of any random shape, okay, the inverse of that means that I have to take every point and its inverse. So the whole set will get inverted into another set. Okay, so the set S1 and S2 are inverses of each other. If like there is a point to point correspondence. Okay. So I mean, in that way, we are generalizing the function. It's not just a point to a point. It can be a set of points going to another set of points. So some objects which we want to study in this way are circles, lines, etc. Okay. And we will find out that what is the inverse of a circle, what is the inverse of a line, and there are some conditions, etc. So we will get to that. Okay. Just to build the intuition a little bit more about this inversion, like in particular, I really want you to get the sense that this is really like a mirror image. Okay, and to get that idea, imagine this situation that so I have a circle. Suppose I have a circle. Okay, so it is passing through some point, some fixed point K. Okay, and on this line I have the point P, and its inverse image is somewhere here. Let's say Q. Okay. So basically, what we have is OP into OQ equal to R square. Now, suppose I keep the point K fixed, okay, and it start to move point O farther and farther. So in other words, I'm increasing the radius of my circle. So maybe if I move point O further, this circle will start to look like this. Okay. In the limiting case, if the point O moves really far, I mean basically at infinity, then do you see that this circle starts to become more and more like a straight line?
Yes.
Yes.
Okay. And now in a straight line, I mean, this is basic physics which you have done in school also, that if your point P, its image is point Q here, and you denote it like this. And everybody understand that this distance is equal to this distance, etc. Things like that. So here, I mean, here the word inverse image in your mirror, we are all familiar with this language. So what we are really doing with inversion is using the same language for a circle, which has a finite radius. Okay, so in that sense, there are a lot of similarities between these two diagrams. Okay, the inverse in a mirror, which is a flat line, and the inverse in a circular image. And I mean, this will help for your intuition. I mean, nothing more than that. This is not a proof or anything, but just to get your intuition trained to this idea of taking the inverse image. Okay, so as such, I mean, if you ask me what do I have to teach in inversion, it's just the definition. As soon as you know this equation, this is the first principle on which everything else can be derived on your own. So if I just leave you for half an hour, 1 hour, and ask you to derive all the properties, you might finish this topic on your own also. But I mean, what I would like to do is guide our discussion towards some important properties. This can be helpful for Olympiad problem solving as such. So I mean, so if you see this worksheet is really this definition of inversion, and everything else is problems. So that is how this topic is really. But so through the problems, you learn the theory automatically. Okay. So with that, I'll suggest you to start trying the problems. So you can try problems A, B, and C to begin with. Okay. And I'll guide you along the way. So it's not just that I'm leaving you to try the problems, but start thinking along these lines. Can you construct the inverse, for example? If I give you a point and a circle, can you construct the inverse with a ruler and compass? And then a harder challenge is, can you do the construction with only compass? Okay, so is the definition clear? What is inversion about?
Yes, sir.
Yes, sir.
Yes.
Okay, so how can we construct the inverse with ruler and compass?
R square is equal to OP into OQ, so we can find
Yes.
OP.
Yes. So I mean the typical Pythagoras kind of setup you can use. If you know any two of the quantities, you can find the third quantity. So suppose you are given the point P and you want to determine point Q. Okay. So basically OQ is nothing but R square upon OP. So if I can do this computation, then I'm done. Now one way to do that is, so I can always use as reference our standard Pythagorean triangle. Okay. So in this diagram, we know that if I call these points A, B, C, D, then BD into DC equal to AD square. So I can draw this diagram on the side. So basically what I will do, I will draw, I know the altitude AD. So this has to be equal to R. And then one of the sides, this has to be equal to OP, for example. Okay. So I'll first draw this triangle ABD, right angle triangle of length R and OP. Then I'll draw altitude 90 degree over here to complete this diagram. And whatever distance I get over here has to be OQ. Something like that. Or there could be many other variations of this idea also. What about only compass? Does anybody have any idea how to do this construction with only compass? So the circle is given to
So
you.
we can.
Yes, go ahead. How do you do that? So for that, do you need the point P inside or outside? Or what is the assumption you are making? Let's start with the P point outside. And by the way, I mean, when the line is not given, so all you have is the point O and P. So now how do we construct the inverse? Okay, unfortunately, this method, I don't have any intuitive way of telling you why you should think of this method. If anybody has a explanation, you can tell me, but this method seems to work. So you take your compass, you put it at point P, okay? You take the radius PO and you draw this arc, okay, with center P. So it will intersect the circle at points A and B. Now you take the radius OA, which is equal to R, and you draw a arc with center A and arc with center B. Okay. So then this point turns out to be the inverse Q. Now, obviously, we have to prove why this is the case. So again, to repeat the construction, so basically OP, as per the construction, OP will be equal to OA and OB. Oh, sorry. PO will be equal to PA and PB. And then center A and B implies that AO equal to PQ and BO equal to PQ. So given all of this information, why does it imply that OP and OQ are inverse, or that OP into OQ equal to R square? So at least whether we have to.
I didn't understand from A and B. How did you construct Q?
So you keep your compass at point A and take the radius AO. So AO is the radius, and I make this arc. And similarly
Okay,
with
sir.
point B and BO, you make another arc.
Okay.
And if you have a compass ready at hand with you, you can try this out quickly to verify that this idea works. Okay, but having verified the idea, we still have to prove. So I'll give you a few minutes to try this out. Okay, so let us erase the arcs and draw lines, then that can help us to track some of the quantities. So for example, what we know is you have these isosceles triangles. That is the first thing that we know. Now, the two marks which I mentioned, by symmetry, you can say that they lie on the line OP, but we haven't proved that yet. For now, I'm just making the assumption that they meet on the line. I mean, to really to prove that the what just happened? Oh, I didn't know this was possible. Anyway. Yeah. So to prove that the two arcs meet on the line OP is also important, because the inversion is not just about the product being equal, but they also have to be collinear. So OQP also has to be shown, but at least this part I'm saying by symmetry it is obvious. So I'm not going into details. You can probably some argument can be worked out using angle chasing. But so the important thing is, why is this true? Why is OP into OQ equal to R square?
Sir, here quadrilateral AOBQ is a rhombus. So
Yes, correct.
diagonals will have to be perpendicular bisectors.
Yes, correct.
So here will uh, OP will bisect AB.
OP will bisect AB, correct.
So Q belongs to OP.
So are you giving the proof of the first part or the second part? I mean, what we want to prove is that OP into OQ equal to OR square, right? So
So second part can be done by similarity. There are two similar triangles.
yeah, okay. But what about the first part?
First part we can say that let the arc with center A and radius OA intersect OP at Q, and then we can prove that Q belongs to arc with center B and radius OB.
Wait, actually, when I means first part and second part, I mean the equation 1 and equation 2. So second part is the collinearity, that I think that I am okay with. First part, the product OP into OQ equal to R square. That is the one I am asking. How do we prove that?
Triangle APO is similar to triangle OAQ.
APO is similar to triangle OAQ. Why is that?
Theorem in triangle AOP.
Yeah, okay. So this is true because they are both isosceles triangle and they have one angle common. Okay. So then what happens?
Sir, then AO upon OQ is equal to AP upon OA, and then cross multiply.
Yeah, okay, fine. So basically APA and OA are corresponding here. So AP upon OA equal to AO upon OQ. Therefore, yes, correct. No, maybe I should take some different pair. PO upon AQ. Yeah, PO upon AQ. Therefore, AP into AQ. Okay, I'm interested in OP into OQ. So if I should take this pair and this pair. Okay, so AO upon OQ equals PO upon AQ. Therefore, if I cross multiply, I'll get OP into OQ equal to AO into AQ, which is equal to R square. Okay, fine.
Sir, we can also do it in another way.
Yeah, tell me.
Sir, if we take the circumcenter of triangle AQP,
Okay.
then angle KAP will be angle AQP minus 90 degree.
Circumcenter of AQP, correct? So I mean, it will lie somewhere here.
Yes, sir.
Okay, so angle KAP, can you repeat?
KAP will be 90 angle AQP minus 90 degree.
AQP minus 90 degrees. Okay.
Sir, in triangle AQO, angle AQO and triangle AOQ, they are going to be 180,
That,
180 minus angle AQP.
yes, correct.
So, sir, angle OAQ will be angle 2 times angle AQP minus 180.
Okay.
Sir, and then sorry, sir, I made a mistake. I wanted to prove that that angle would be 90 degrees. KAO.
No, you might be on the right track, like the thing. And I think what you're trying to use is tangent secant theorem in some way. I mean, see,
Yes.
basically, if I show OA is tangent to this circle which you're talking about, so I mean, the circle in consideration is circumcircle of AQP. So if OA is tangent, then we will done. So if we prove that angle OAQ is equal to this angle, then actually this is directly done by similarity, right? So this is also one more proof. I mean, the same similarity which we wrote earlier, that gives that these two orange angles are also equal. So I think that is also sufficient to prove this. Okay. Yeah, I think and then one or two other ideas may also be there. But anyway, so it's interesting that you can do this inversion with only compost. One caveat is that we took point P outside the circle. If the point P is inside the circle, this construction doesn't work, right? Because then the starting point of considering the circle with radius PO, I mean, this arc intersecting the circle was the basic point. If you have a diagram like, let's say, O is here and P is here. Now the circle with arc with radius PO doesn't intersect your main circle at all. So in this case, this approach doesn't work, but there are some tricks you can use. So one thing which you will notice is that as per the definition of inversion, what happens when a point, so if point Q is here, its inverse is here. Suppose you double the distance of point Q. So you take the point Q twice as far. So let's say Q dash. Okay. Then what will the point P move? Where will P go? So this distance is equal. So where will the inverse of the Q dash lie?
Sir,
More closer
midpoint
to
of OP.
Midpoint. Basically, among these two quantities, if you double one quantity, the other quantity has to come by half. Okay. So the you can basically move 1 point farther and farther, like double, 4, 8, any power of 2, and the inverse will keep on moving closer and closer to the center by the same factor of the power of 2. So what you can do is, if your point P is here, you want to find the inverse of P wherever it is. So you first keep on doubling the distance. So if I call this P0, I double it, I get P1. Okay. Then I again double it, I get P2, etc. So I keep doing that until the point moves outside the circle. Okay. Then I find the inverse of this point. So the P2 inverse may be some Q2 over here. And then by the same logic, if P2 and Q2 are inverses, then the inverse of P1 will be double. So Q1 will be somewhere here. And again, if P1, Q1 are inverses, then inverse of P0 will again be double. Okay, so you can do this, but for that you need to know how to double. I mean, if I have a 2 points A and B, how do I find the point C in this way, such that they are equal in length using only compass? Do you know how to do that? So given A and B, construct C such that B is the midpoint of AB, the midpoint of AC, using only compass. I mean, with center B, you can draw a circle. You don't know where point C is. So with B as the center, you can draw a circle, but you are not drawn the line AB. So where is point C located? How can you determine it only compass?
So from point A, take the radius AB and keep making marks on that circle.
Yeah, exactly.
It's a hexagon. So then see.
Yeah, correct.
Opposite.
So I mean, if I take this radius, I'll get a point P, and I'll continue this pattern. So from point P and PP radius, I'll get another mark, and finally with QP, I'll get points. So basically, we exploit the fact that the hexagon, the regular hexagon, is nicely inscribed in this circle, so you can get the points. Yeah. But anyway, I'm just giving you a taste of a big result that you can do later on, which is that every construction which you can do with ruler and compass, you can do with only compass. Okay. So this is a very big result, but we will work towards it step by step. Anyway, so I mean, there is not much connection with this with inversion, but it's nice to know. Okay, so moving on to the next question, question B. So question B is actually just an important observation about how inverses work if you change the radius. So if you keep the center of inversion constant but only change the radius, what happens to the inverse image? So that is, I think, important to know. So suppose you have a circle, okay, and some object S, okay, of any random shape, okay. So the inverse of this object will be some S1. Okay. Suppose you have another circle of the same center O but a different radius. Okay. And you invert the same object S in this red circle. Okay. So you'll get an object S2. Okay. So if you take any particular point, let's say you consider a point P over here. Okay, and its inverse images are P1 and P2, and the two radii are R1 and R2. Okay, so what are the equations we have? So P and P1 are inverses with respect to the first circle with center O and radius R1, So therefore, OP into OP1 square equal to R1 square. OP into OP1 not square. Okay. Then P and P2 are also inverses, but in a different radius. So therefore, we get the equation OP into OP2 equal to R2 square. So if you put these two together, what is the connection of P1 and P2? So if you eliminate P from the equation, you will see that the ratio OP1 upon OP2 is R1 square upon R2 square, which is a constant basically. So in other words, as the point P moves on this set, so point P will move on the set S. P1 and P2 are going to move, but all the time the ratio is going to be constant between OP1 and OP2. Okay, so what this means that S1 and S2 are similar, and I mean they are related to each other by just this fraction. What there is the ratio R1 upon R2 square. What does this mean? It means that taking the inverse image, the shape of the inverse object doesn't depend on the radius. So you can change the radius, but the shape remains constant. And this is going to be important when you do problem solving, because many times, I mean, how we are going to apply inversion in problems? We are going to invert the entire diagram with some circle. And so what this is saying is that the radius of that circle doesn't matter. I mean, if you take a circle with double radius, all it will do is shrink your diagram by half or vice versa. But the relative position of object doesn't change if you change the radius. So that is what this property really means. So in a while solving the problem, of course, you will write that we invert the diagram with respect to a circle centered at some point O. I mean, assuming there is some point O in your diagram. So you are inverting with respect to circle centered at O and any radius. So I mean the radius can be anything. So the radius doesn't really matter. It's just a scaling factor. Okay. So that is an important thing to understand about inversion. In a way, you can relate this to the mirror image concept. So I mean, going back to the mirror image, this analogy which I talked about. So if I have an object over here, in a way you can think of changing the radius as shifting the mirror parallel to itself. So if I have some object here, okay, its mirror image will look like this. If I take another mirror of this parallel to itself, but just shifted in space, so instead of here, let us say I have a mirror here. In this mirror also the inverse image of this. So you see, obviously these two are going to be not only similar, but in fact congruent. So all you have done is shifted the object to the left or right, but the shape of the object doesn't change. So in many ways, this is similar. So changing the radius only changes the scaling factor of the diagram, but doesn't change the relative position of the objects. Okay. So anyway, we'll see this in practice when we solve the problem, but it's an important property to take care of. Okay, so now comes the real part of discovery, where we find out what is the inverse of various objects. So as I said, we are interested in lines and circles. So when you are talking about lines, we have to take two cases: a line which passes through the center of inversion and a line which doesn't pass through the center of inversion. Okay, and in both cases, so in the first case, a line which passes through the center is its own inverse image. So if you have a circle, this part I think is relatively easy to see, because basically the collinearity ensures that. So if point P is the inverse of point Q and vice versa, then you see the entire segment OA. So OA where O is not, there is no symbol for this, but basically open interval from O to A. So I'm referring to the segment OA minus the point O itself, because we know O has no inverse. Okay, so this segment you will see has a one-to-one correspondence with the this ray which goes from A to infinity. Okay, again the point at infinity doesn't have any inverse. So like this point is inverse of this point is inverse of this point, etc. So this whole line, this whole segment gets mapped to this whole segment. And similarly on the left side, so this whole segment on the left side is the inverse of this whole part. And the point lying on the circle is its own inverse, obviously. So you see how this whole line is its own inverse image. Is that clear?
Yes, sir.
Yeah. So the mapping is quite of beat, or what you can say. Understand how the line gets chopped up into various segments and each segment gets mapped differently. So this was the easy case. But what if there is a line not passing through the center of inversion? Okay. So suppose you have a circle and any line L which doesn't pass through the center of inversion. So what will happen to this line? So again, if I take every point on this line and I take its inverse, what happens to this inverse? So as the point P moves, this inverse point will also move. But what is the locus of that point Q? Okay, I'll give you a few minutes to think. Okay, so any idea what that locus of Q will be?
Sir, it will be a circle.
Circle, correct. And how will you determine that circle?
Sir, we can consider 3 more points on line L
Okay.
and their inverses, and then we can prove that they are that those those 4 points are concyclic.
Which 4 points?
The inverses of the
Okay,
other
okay.
points.
Okay, so if we have P1, P2, P3, P4, and their inverses Q1, Q2, Q3, Q4, then all those 4 QI are concyclic. Okay. Is there any other way of saying what that line, what that circle is?
The circle also passes through O.
Circle also passes through O, correct. So if you imagine what happens if the point P goes farther and farther on this line L, right? If I take the point P on this line farther and farther, then the distance OP keeps on increasing. So naturally the distance OQ keeps on decreasing, and in the limiting case, the OQ will be very close to 0. So in that way, that point Q, whatever is the locus of point Q, it has to pass through the center O. At least that part is clear. But now on the other direction, can you think what is the position of P where OP is the smallest? So what is the position of P where OP is the smallest? It is the perpendicular.
Perpendicular from O1 P.
So the perpendicular from O on the line L. So if I call this position A, okay. So then if this is where P is closest, then it will also be the position for which the inverse Q will be the farthest from point O because of the inverse nature. So then if I consider the inverse of point A, let us say it is a point B over here. Okay. So then OA into OB is equal to R square. And now for any other position of the point, like what I've shown here, so OP into OQ is also equal to R square. So what can you say about the 4 points A, P, B, and Q? Okay. So OA into OB is equal to OP into OQ. Therefore, A, P, B, Q are cyclic, correct? And if that is the case, what about angle OQB?
90 degree.
It is 90 degree, because if this is 90, then this is also 90. So then what is the locus of point Q now? Because see, if the line is fixed, then point A is fixed and point B is also fixed. So where does point Q lie?
Circle with diameter OB.
Circle with diameter OB. Okay. And I mean, whenever we talk about locus, it has to be if and only if. So what we have shown is if there is a point P on the line L, its inverse lies on the circular diameter OB. We also have to show the converse, that suppose I take any point on this circle, okay, like Q. Why is it, or rather, let's take another point R over here. Okay. So the inverse of R should also lie on the line L. Only then the argument is complete, but it's easy to see that, because if point R lies here again by 90 degrees, this is a cyclic quadrilateral. So obviously OR into OS will be equal to the same, R square. Okay, so you can show the if and only if part easily, but it's important for completion. Okay, so basically, if you see what's happening, this line L is being inverted into a circle passing through O. And I mean, in this case, I took a line which is not intersecting our main circle at all. Okay, so that is why. So again, you see how that mirror image thing is happening very nicely. So all the points outside the circle are getting mapped to points inside the circle. So let me just modify the diagram and consider the case when my line is intersecting the circle. Okay, so in this case, what will happen? It is still a circle. So the inverse will still be a circle, but not only will it be a circle, these 2 points where our line is intersecting the main circle, these are self inverses. So then in this case, the inverse image of this line will pass through the point D and E also. Okay, so in this case, what the diagram will look like? So again, if I take the point A over here, inverse of point A will be some point B, and the locus is a circle of diameter OB, but that is also the circle passing through D and E. Okay, So it is not hard to see that basically we have Pythagoras kind of setup over here. Therefore, OA into OB equal to OD square, which is R square. What I want you to start to do is visualize how when I move any object in the plane, how does it inverse image also move? So when this line L was outside the circle, the inverse was like this. As the line starts moving closer and closer to the circle, this inverse circle also grows in the radius. When this line L touches the circle, so it is tangent at a point, then the inverse image is also tangent at the same point. Then when the line starts moving inside the circle, so it has some point of intersection, then the inverse image also starts having the same points. And if I continue this way, when the point, the line is very close to the center, so then the inverse image is also going to be a circle of a very big radius. And eventually when the line moves exactly through the center, then this circle of very big radius also coincides with that line. Okay. So there are all of these dynamics which are happening. I mean, it's hard for me to draw every case on the paper, but I mean, you can easily set this up in GeoGebra and see the animation. Okay, but get a sense of how when this line moves, how its inverse image moves. Then you will start to realize that I mean, these are not really separate cases. Like the line passing through O and not passing through O is not really a separate case. It is just I mean, the inverse is a circle of infinite radius in that case. That is all that is happening. Okay, so is the line case clear? What is the inverse of any line? So then the next consideration is what about a circle? So in other words, so my circle of inversion is given and I have any other arbitrary circle in the plane and I want to consider its inverse image. Now based on what we already studied, suppose I start with the circle passing through the center O. What will be the inverse of this circle?
Line.
It has to be a line because that is the nature of inversion. It is there is a name for such operation, by the way. It is called an involution. Okay, so if I just go back, scroll all the way back to the start of this topic, when I talked about the functions. So in general, any geometric transformation has a inverse map also. Okay, let us take some very simple transformation like move every function f which moves every point to the right. So what is right is not clear, but I just say to the right by 1 unit. Okay. So let's say I mean this graph paper, this is 1 unit for me. Okay. So basically, if a point P is over here, this f of P moves it to the right by 1 unit. So what is the inverse of this operation? So f inverse will move the point Q back to P. So it moves the point to each point of the plane back to the left. So basically, for every function, for every transformation, there also exists an inverse transformation. And this is true only for bijections, but I think for the most part, whatever transformation we study are kind of bijections. So every function has that inverse image. Inversion is special in that it is its own inverse image. So if you apply inversion twice, you get back the original object. Just as what happened in the definition. So when you took the inverse of P, we got Q. When we take the inverse of Q, we get P back again. Okay, so this self-inverse, it is its own inverse, which is a very important property. And because of this, what we can say is that what we did just now, we proved just now that a line has an inverse, which is a circle passing through point O. Therefore, the inverse of a circle passing through point O will be a line. Okay, so this duality is important, that any line in the plane and a circle passing through O. Okay. So therefore, any circle passing through O will have a line. And how to construct this line? Again, if you take the diameter of your circle and you find the inverse of this point. Okay, so wherever is the inverse of this point, if I call it A, then the perpendicular line to OA, this will be the line. And again, how to prove this? If you take any other point P on this circle, then I have to prove that the inverse of point P goes onto this line. It's exactly the same proof that we did just now. There's nothing different at all. Okay, so any circle passing through the center of inversion becomes a line. So now the case to be considered is, what about a circle not passing through the center of inversion? Okay. So suppose you have any arbitrary circle like this, which is not passing through the center of inversion, then what is the inverse of this circle? That is the question. Okay. But is this part clear? Is this duality understood? That
Yes, sir.
going from line to the circle and vice versa, they can be done. Oh, sorry, I didn't see on WhatsApp. Dev, have you joined the meeting? He posted on WhatsApp to share the link to the meeting. Okay, so any ideas what you can do for a circle not passing through the center of inversion? One thing is clear, if a circle is inside our given circle, its inverse will go outside and vice versa. But roughly speaking, do you have an intuition? So suppose I have a point P over here and it is moving on this inner circle. So as you can imagine, the distance OP will keep varying between the minimum and maximum.
It'll become a circle again.
It should be a circle, right? Vaguely you can get some idea that it should be a circle. But why? Why is it a circle? We don't know yet. But suppose, assume that it is a circle. Assume that we know it is going to be a circle. How would you try to construct that circle?
We can construct the inverse of the center of the second circle with respect to the first center.
Okay, so if the center is O1, then you will consider the inverse of O1.
Yes, sir.
Okay, but why do you feel that the center will go to the center?
So we
When
can
we are
consider.
interested in the points on the circle. We cannot say anything about the center as such.
So we can take the inverse of any 3 points and draw the circle.
Yeah, so we can take the inverse of any 3 points and draw the circle. Or another way of doing it is, instead of taking 3 points, you say I can do it with only 2 points if I choose the diameter.
Yes, sir.
Yes.
Okay, so I know that and by symmetry or whatever is going to be the inverse image, it will be symmetric along this line. So why don't I consider the points A and B over here? Okay, and I take their inverse. So what will be the order, by the way? If B is farther from O, its inverse will be closer. So inverse of B, if I call it B1, it may lie somewhere here, and A, its inverse will be A1. So everything is going to be reversed. And hopefully the circle with diameter A1, B1 will be the inverse of my original circle. That is what I hope. So even though you have not proved that this is the inverse, if we have to construct it, we at least have some idea how we can construct the inverse. Okay, so this is the construction that, so we consider the inverses of inverse B1 A1 of B comma A respectively. Okay, and now so what we are claiming is that, by the way, you will find out that it's not true, the center doesn't go to the center, unfortunately. So it is not true that the center, if I call the center O1 and O2, the O1 and O2 are not inverses of each other, unfortunately. But now if I have any point P, this is what I have to prove. That if I have a point P over here, and if I extend that line and let it meet at point P over here, and again you see how I'm taking the correspondence. The farther point P on the, because this line OP is intersecting the first circle in 2 points, but the you see how I'm corresponding the 2 points. I should call this P1. Okay, so P and P1 will be inverses and Q and Q1 will be inverses. So the order is getting reversed. Okay, so what we have to prove is that OP into OP1 is equal to R square. If we prove that, then we are done. And what is given to us is this how we constructed P1 in the first place. So we took the circle with diameter A1 B1, where A1 B1 are themselves inverses. So basically what is given to us is that because A and A1 are inverses, so we know OA into OA1 is equal to R square. So this is what we have available to us, and with this we have to prove this. Okay, so let me break up this problem into several small steps which you can try to prove. So I don't know if it is clear from this diagram or not, but as it turns out, if I call these two circles gamma 1 and gamma 2,
So we can use power of point in both the circles.
sorry,
So we can use power of point in both the circles. O into OB is equal to OP into OQ.
okay, how do you use that? What does that give us?
So that I didn't do, I should try.
Yeah, okay, give it a try. I mean, PowerPoint can be useful.
So we can prove PP1 B1B is a cyclic quadrilateral.
P1, yes. If we prove that, we should be done. How do you prove that?
So I'm still trying to do that, but I thought
Okay.
of it.
Yeah. I mean, that is a right approach. If you are able to prove that BP P1 B1 is cyclic, then we are done. Because then this would imply that OP into OP1 equal to OB into OB1, which we already know equal to R square. Okay. So as an intermediate step before we try to do this, there is a one thing which you can do which is slightly simpler is so prove that O is the center of not the sorry I should say O is the external center of similitude for gamma 1 and gamma 2. Okay, so are you aware of what is the meaning of this phrase, external center of similitude?
No, sir.
No,
Oh,
sir.
sir.
Okay, so forget this problem for a while. Maybe some basic theory that we need to know. If you have any two circles, right? Okay, with center O1, O2 and some radius R1, R2. So we all know that we can draw tangents, common tangents to these two circles, external and internal common tangents. Okay. So suppose I draw the external common tangent to both the two circles, and do you know the construction for this with ruler and compass?
No.
Okay. So if you don't know that, you can revise it from somewhere. But suppose I draw the external common tangent and let it meet this line O1 or 2 at some point T. Okay. So then what can you say about the ratio O1T upon TO2?
R1 upon R2.
Is R1 upon R2 because we have two similar triangles, right? O180 and O280 are going to be similar. O2BT. So by similarity, you get this. So in other words, T is dividing O1 or 2 externally in the ratio R1 is to R2. Similarly, suppose I draw internal tangent, internal common tangent. Then I get some point S. Do you see that O1 is, and actually for keeping everything directed, I can call this minus R1 upon R2, because if you see TO2 and O1T are going to have opposite signs. Do you see that similarly for the point S also this is true?
Yes.
Okay, so in other words, what are point S and T doing? S and T divide,
So O1 SO2 T.
sorry, can you repeat that?
So O1 is O2 and T are harmonic points.
They are harmonic, correct, because S and T divide the segment O1 O2 internally and externally in the same ratio, R1 is to R2. Therefore, the points O1 O2 and ST are harmonic. Okay, so these points S and T are called the centers of similitude of the circles gamma 1 and gamma 2. Okay, sorry, actually I'm going to make a big detour here. If you don't know this property, there are a lot of interesting things that are related to this, which I think they're all worth talking about. We will return to this inversion problem later on, but I think there's a lot of other important things to be covered here. Okay, so let me take 10-15 minutes to cover this. Maybe we'll have to continue the inversion part next time, but that is okay. I think this is very important. Okay, so these S and T are called centers of similitude, and as you can imagine, because similarly like what you have internal and external common tangent, you can call S as the internal center and T as the external center. So any two non-concentric circles, you can do this. If O1 and O2 coincide, then none of this applies. But as long as, even if the circles are intersecting, or even if one circle is entirely inside another circle, even then, so now if one circle is inside another circle, there is no question of drawing tangents, but you can still construct the points on this line, okay, such that maybe the T will not lie here. I don't know where the point T will lie, somewhere here. So you can still construct the points S and T such that these ratios are preserved. Okay, so that this, I mean, the tangents is one way of drawing that, but you can directly construct the point S and T knowing this ratio also. Okay, so in any way you can do that, you get the points S and T. Okay, what is the importance of this point S and T? So in the word similitude is inherently the word similarity being used. Now we all know about two triangles being similar, but what about two circles being similar? In a way, that concept seems very silly, that a circle S1 is similar to circle S2. What is there to be similar about? But in a way, you can think of these as centers of similarity also. I mean, just going to this diagram again, where we draw the tangents, you see there is some sense of correspondence that this point O1 and O2 are corresponding, and this point A and B are also corresponding. And if I draw any other line through point D, okay, then whatever points I get, suppose I call this point P and Q, you see that basically this O2P and O1Q, they will be parallel. So in a way, as the point P moves on this circle, first circle, point Q will also move on the second circle. So there is a one-to-one correspondence between all the points on the two circles. Okay, so in that sense, these points S and T are the points of similarity also for the two circles. So anything that is happening in one circle can be translated to the other circle. Like for example, if I have a triangle here, I can take every point, so the three vertices of my triangle, I can take their images under this homothety. So this point will go somewhere here. So you can see I can draw a triangle over here, which will be parallel and similar to this first triangle. Are you following me?
Yes, sir.
Okay. So there are a lot of things like this. So like every point will be corresponding on these two circles. And so all of this I am showing with the external center. Similar thing will happen with the internal center also. In the internal center, everything gets rotated, inverted. Now I should be careful with using the word inverted. That is not the inversion we are talking about, but literally it will be the mirror image. So if I have any object in the first triangle, let's say any triangle like this, and I take the images with respect to the internal center of similitude, then you see, if I just join the lines, then this point will go somewhere here. Okay, the diagram is not very good, but basically what you see is that the whole triangle has been reflected as if by like a mirror image. Okay, so not a mirror image also, but this circle, triangle ABC has become triangle A1B1C1. Okay, so in the previous case, if you see the original triangle, this red triangle, and this image, they were parallel and had the same orientation. Whereas here, the segments are still parallel. So BC is still parallel to B1C1, but it is flipped. It's like a 180-degree rotated image. I mean, in a way, you can see this is like the diagram you draw for retina, right? In an eye. So the lens of the eye, if there is an object outside, like a tree, when it goes to the lens of our eye, on the retina, it forms an inverse image of the tree. In a very similar way, what this internal center of similitude is doing that.
So this is like homothetic transformation, right?
This is homothetic, correct. This is homothetic with ratio R1. So if I call that radii R1 and R2, then this is the homothetic with ratio R2 upon R1, or rather minus R2 upon R1, because the inversion is happening. And if I take the external center, then it is plus R2 upon R1. Okay. So actually, I didn't know whether you are aware of the homothetic transformation idea or not. I don't know. Maybe everybody is not aware of this concept of homothetic.
So we have learned it.
You have learned it.
Yes, sir, in the
Okay,
workshop.
that's good. Okay, then another name for this, I was then for no reason I was avoiding to use the word. They're also called centers of homotheity. Okay? So similar to homotheity, they are like both words are perfectly okay. Okay? So these are the centers of homotheity for these two circles. And then I mean, okay, then I don't have to spend much time on this. Then you know some of these ideas. In a triangle, do you know any two circles which are homothetic in a standard form?
9-point circle and
8-point
Yes.
circle and 9-point circle.
9-point circle and circumcircle. And what are the two centers of homotheity?
sir, ONH.
So one
O and H, and with the ratio to 1 upon 2 and minus half. Okay, then you know all these things. I thought you haven't studied this at all. Okay, so that's what I'm referring to. So maybe I mean going back to the diagram, what I want you to prove is that O is the center of homotheity for these two circles. Okay, so let me just draw. I mean, there are a lot of things happening in the diagram. So let me just draw some part of it again. So this is our center of circle of inversion. And I mean, knowing the fact that they are going to be homothetic, so I can be a little bit more accurate in drawing the other circle. So maybe something like this. So now, again, if I consider the diameter, okay, so points A, B, and the inverse is B1 and A1. So even before getting to the point P, which is the arbitrary point, just given this much information also, first thing we have to prove is the O is the center, external center of homotheity. For the circles gamma 1 and gamma 2. Okay, so this is the first step to be proven. And where what is given to us again that A1 and B1 are inverses. So if I call the radii of my two circles R1 and R2, then what is enough to show? What fact, if I show, will imply that O is the center of homothety? And again, given OA to O1, OA1 equal to OB, OB1, which is equal to R square. So my claim is that, suppose I prove, again, if you understood the whole thing, I unfortunately erased the image, but what the homothety implies that there is a one-to-one correspondence between the two objects. So in this diagram, do you see that A and B1 will be corresponding to each other under this homothety?
Yes.
So then what should be the ratio AO upon OB1B? I mean, this is to prove that we are not proved it, but if we show that this ratio is equal to something, then we are done. So what is that something?
Sir, will it be BO on OA1?
Sorry, I couldn't hear you properly.
Sir, will it be BO on OA1?
BOA1. BO and OA1.
Sir, R1 upon R2.
Ha, correct. Okay, yeah. So I got it. So you are saying this is the BO upon OA1 equal to R1 upon R2. That is correct. So if we show all of these three things, then we are definitely, I mean, we have proven that O is the point we are interested in. As it turns out, we don't have to show both of them. Even if we show one of them, that is enough. Okay, so if we show AO upon OB1 equal to R1 upon R2, then also we are done. Because basically there is only going to be a unique point on this line which has the ratio R1 upon R2, and that has to be that center of homotopy. So how do we do this?
Sir, we can substitute O1, O and O2, O plus R1 and R2. So we can eliminate OA and OB1 and instead substitute O1, O1, O2 and R1 and R2.
I didn't follow. So what should I write?
For AO, we can write O1, O minus R1. And for OB, we can
O1
write
O minus R1. So in the given term, or what you have to prove? Where are you substituting this?
in these ratios.
Okay, in these ratios. So instead of AO, what should I write?
O1 minus R1.
O1 minus R1. So to prove that, instead of AO, have O1 minus R1. Okay, continue. And similarly, OB1 will be replaced by O2 minus R2. Is that your idea?
Yes, sir.
So this is what we have to prove. Then what do we do?
Sir, then by componendo dividendo, we just have to prove that OO1 upon OO2 is R1 upon R2. And then we can...
Yes, actually it's not comparative window, it's the theorem of equal ratios. So basically, I mean, this is if and only if OO1 upon OO2 equal to R1 by R2 by theorem of equal ratios, which you would have used when you did Seva's theorem proof.
Yes.
Okay. So how do we prove this?
Sir, we can equate OA into OO1. So OA1 is equal to OB into OB1. And again, if we substitute, then if
Okay, so here again substitute everything by this will be O1 minus R1, etc. etc.
yes,
Sir,
sir,
if we
this
cross
is
multiply, minus R1, R2 will get cancelled on both sides and will remain as O1, R2 will be O2, R1, then O1 upon O2 will be R1 upon R2.
yes, sir. By simplifying, we get the required
Yes,
answer.
sir.
Okay, so if I continue to simplify this, I get a desired thing. That's what you're saying.
Yes, sir.
Yes.
Okay, so let me just try that quickly. I have a slightly different approach, but maybe we are going to do the same thing. So here it will be OO2 plus R2 equal to OB. OB is OO1 plus R1 and OB1 is OO2 minus R2. Okay, so if I expand out everything, I can see some things are going to cancel, like OO1 into OO2 will cancel out. R1, R2 will also cancel out. I think only the cross terms will survive. So I will get OO1 into R2 minus OO2 into R1 equal to OO1 minus, yeah, and I think if I take everything on one side, basically this means OO1 into R2 equal to OO2 into R1. This is exactly equal to this. Okay, so I mean, I hope everybody followed this proof. Basically, what we were doing so far is we know that these two are equal. OA into OA1. This statement we know. So if we equate the two and we substitute, we basically use OO1 and OO2 as the fundamental variables and put everything in terms of these distances and R1, R2. And then we expand, we simplify, we get this. And this is equivalent to this expression. Okay. I mean, maybe I was also doing the same thing. I have a slightly different way of approaching things, maybe. So what I do is I start with these two expressions, 1 and 2, which is given. So if I equate them again, and if I so OA into OA1 equal to OB into OB1, this is given. Then what I do is I rearrange this as fractions. So I write this as OA upon OB1, rather OA upon OB equal to OB1 upon OA1. Okay. So my objective is to, oh sorry, I mean this one. If I just simply rearrange this, I get OA upon OB1 equal to OB upon OA1. So this is the first part which I wanted to prove, that these two are equal. That is getting solved here. But I can continue to work on this. And how do I get R1 and R2 out of this? So for that, we are missing this step. And so then by theorem of equal ratio, this is also equal to OA, OB minus OA upon OA1 minus OB1. And OB minus OA, if you see the diagram, is nothing but the diameter of the first circle, OB minus OA. That is twice R1. And similarly, OA1 minus OB1 is twice R2. This is twice R1 upon twice R2, which is R1 upon R2. Okay, so this was my proof. Maybe in some ways it might be similar to what you also did. Okay, so now all of these things I use the theorem of equal ratios. So I hope everybody is aware of this property.
Yes, sir. Theorem of equal ratio.
You must have done it definitely when you did Seva's theorem proof. Okay. Yeah. So what we have proved is that O is the center of homotheity for these two circles. Now given that information, now you can go back and try to prove this. Finally, what you wanted to prove is this point P and P1 are inverses of each other. So, for example, one I'll just give the outline of one proof. somebody wanted to show that these four are cyclic, B, P, P1 and B1. But now if they are O is the center of homothety, then what can you say about O2 P1 and O1 Q? They don't appear it, but they have to be parallel.
Yes. Yeah.
Yes, sir.
And
Yes.
not only that, so even P1 B1 will be parallel to AQ.
Yes.
So, and we already know AQPB is cyclic. So we can use the angles to chase the fact that even these four are cyclic, the one which we want.
Yes, sir.
So I think hopefully you can see the intermediate steps there. Okay. So anyway, I think we are almost out of time. So I'll encourage you to try out this part. And so basically with that, what we have concluded is the first exploration, that basic objects in the plane like lines and circles, we know how to find their inverse from any with respect to any given circle. Okay, so armed with that basic knowledge, then again, if you look at the problem sheet, and also I've uploaded this to the shared Google Drive, then a lot of other properties emerge with this basic information. Okay, in particular, you'll see that orthogonality is a important thing. Orthogonal circles are self-inverse of each other, and things like that. So if you are interested, you can try and prove all of these things on your own. That will save us some time in the next lecture. But yeah, so anyway, I hope this was a sort of introduction to how inversion works, and then we will actually do some problem solving. In fact, you'll see there are many IMO shortlist problems which we are going to do using inversion. So this is an important technique for a lot of ideas. And then after this, the topic poles and polar will also be similarly useful. And all of this is connected to the harmonic points that we have discussed earlier. Okay, that's all for now. Unfortunately, I didn't get time to discuss a puzzle or anything. Maybe just quickly in 5 minutes, I'll share something with you. So I actually want to continue on the idea of binary numbers, which we used last time. So we were doing the problem of the poison bottle in 1,000 bottles, and so where we saw how we can create a very nice table of all the binary numbers, and that gives us precisely which bottle is to be given to which set of prisoners. And the way it works out is that uniquely every prisoner or every bottle is given to only one particular combination of prisoners. So that is how we figured out that which of the bottle is poison. There are lots of other applications of binary numbers also, and they all come from the idea of powers of two in one way or the other. So here is one other interesting example. And this is a very practical example, by the way. I mean, we use it all the time. I'll talk more about how we are using it now also. When we are using Zoom online, we are using this idea all the time. I mean, this is how computers work actually. So whenever you write any Word document, let's say in a Word document, you write the letter hello, word hello. Internally, what the computer does is it stores every digit as a sequence of binary numbers, and typically it uses 8 bits. So that means the 8 sequences of zeros and ones, which we call 1 byte. Okay. So for example, the word letter H could be coded as 001011. Some combination of ones and zeros. There is a table to show that mapping. Okay, so every letter gets written in some binary format. Now, if you take any Word document, you do this. You type maybe 1,000 characters. Okay, so if you type a document having 1,000 characters, okay, and each character requires 1 byte of storage, then you'll expect that a file having 1,000 characters will require 1,000 bytes to store. So its size on the file will be 1 KB. You can try it out. Actually, the size of the file will be much smaller than 1 KB. So the whole question is, how are you able to represent the information with using less number of bytes? Okay. In other words, what I'm talking about is compression. So we all know about the zip file. So zip compression. You can take a lot of data and you zip it, you get a small file. So it seems like almost a magic that you take a lot of ones and zeros and there is a special function of zipping which can convert this ones and zeros into much smaller data set. Maybe like 1 MB of data will be compressed into only 1 KB. And later on, when you want to get your files back, you can do that, right? You can unzip your data, you will get everything back, so you don't lose anything. So how are you able to take information and sort of magically compress it into less amount of storage? Okay, so that is one very interesting application of binary numbers, and we'll see that in more detail in coming lectures. But just to give an idea of how we can achieve this. So here what I showed you is that every symbol I'm going to use 8 bits to represent. So that is how the word HELLO what represents it somehow. But I know in English language that some characters appear more frequently than others, like vowels like A, E, I, O, U. We all know that these are going to appear much more frequently. So the idea is, why don't, instead of using 8 bits to represent every character, I can use less bits to represent this. For example, if and there are 5 characters, so I require minimum 3 bits. Okay, so for example, in some way I could say A000, E001, etc. Okay, so for these 5 characters, I only use 3 bits. Okay, and for all the other characters, I still continue to use 8 bits. Okay, so in this way, at least you see one way I have tried to achieve some compression, that I don't require the number of characters into 8 bits is not required. I can do with much lesser than that limit by using some clever mapping like this. So I mean, the whole question is to figure out, this is just I'm using my knowledge of English language to come up with this mapping, but you can do a bit more complicated way of figuring out like how many bits are to be assigned to every character, so that you represent the same data in less amount of storage. And the same thing is applicable in every domain. So this was just text, but images, music, video, everything has the same principle, that if you have an image of 1000 cross 1000 pixels, not every pixel is important. Like for example, you are looking at my slide right now. You see most of the area is completely white. So why should I send white 1000 times? So why? It doesn't make sense. So what Zoom or any other application it does is it compresses all those whites into something much simpler to transmit. Okay. So all of this is based on binary arithmetic, and so that is what we are going to study next time. So I'll just give you a quick flavor of where we are going with this binary numbers. Okay, I think we are already out of time, so that's all for now. Thank you. Bye.
Bye.
Thank you, sir.
Thank you.
Sir, I am solving workbooks like an excursion in mathematics and
Okay.
then elementary number theory. So I have some doubts in them.
Okay.
So how
Yeah, actually I'm online right now. So if you want, we can discuss them, or if you want, you can send them to me on WhatsApp. Then I can take them. So what kind of doubts do you have?
there are some in geometry and algebra.